This is the fourth lesson in the module Magnetism and Electricity. This will be covering the magnetism and induction component of this module. Here is the magnetic basic knowledge that you need to know. Magnets are substances that produce magnetic fields and are attracted to ferromagnetic substances. Iron is an example of a magnetic substance. Magnets have two poles, north and south, or areas where magnetic fields are the strongest. The north pole is defined as the end of the magnet that is attracted to the north geographical pole of the Earth, south magnetic pole of the Earth. The south pole of a magnetic would be attracted to the south geographic pole of the Earth. So it's the north pole of the Earth, so it's opposites. Any moving charge creates a magnetic field. If there are pairs in the fields, that will cancel because they are spinning in opposite directions. When magnetic fields line up in areas, these substances are called domains. And if domains line up together, then we have something called a magnet. So an example is an iron, which is a ferromagnetic material. And when it's placed in a magnetic field, then it will act as a magnet, because those domains in the iron will be lined up. Remember that a magnetic field is three-dimensional. So when you look at it on the picture right here, you see lines coming out, but remember that the lines are going to be coming off the screen back into the screen, as well as going past your screen back into it. So it's more of a sphere than a two-dimensional shape. The arrows point in the direction of a force would be applied to the north pole. Remember that opposite poles attract, so north is going to be attracted to south and south is going to be attracted to north. A compass is a tiny magnet that is suspended so it is free to rotate and align with the magnetic field of the Earth. The north and south magnetic poles have flipped during the history of the Earth, and scientists are not really sure why. Here is the equation that we will use. Motion, field, and force will mainly be perpendicular to each other, except if noted problem otherwise. So if there is a angle noted in the problem, that's where you are going to use this part. And if it's not noted, then please assume that it is perpendicular. Q is the charge of coulombs, V is the velocity of charge, theta, my angle, is the angle between V and B is the magnetic field. The unit for a magnetic field is Telsa, which is represented with a T. You have to remember about the right-hand rules. This is trying to find the direction of the force of the charged object is perpendicular to the plane formed by the direction of the velocity and the magnetic field. The right-hand rule. First, you're going to point your fingers in the direction of the magnetic field. So this is what we have here. Then you're going to point your thumb in the direction of the velocity, which we have in the green arrow. And then your palm is going to point in the direction of the force. So we have this perpendicular here. Remember, a negative charge will have a force in the opposite direction. This is called the first right-hand rule. All wires that produce electricity have a magnetic field. We see this if you hold a compass near a wire that has an electric current running through it. The magnet will be affected. The compass will be affected. The strength of the field is directly proportional to the current, and the direction is determined by a second-hand rule. And what you see here is the second-hand rule. You have your thumb pointing in the direction of the current. Then you have your fingers, which are going to curl around and point the direction of the field. So you're going to have this circular motion around think about three-dimensionally. Another way to write this is showing this circle with an X. That's indicating that the field is pointing into the paper or the screen. And then the circle with the dot means that it is coming out of the screen, so it's circling this way. If we place a wire in a coil, then we can produce an electromagnet. The strength of the electromagnet depends on number of coils of wire and the current in the wire and the material that make up the core. Michael Faraday proved that when a magnet was moved into a coil wire, a current would produce or induced. In other words, he determined that the change in magnetic field across a wire would induce a current. This is basically how generators produce electricity. And the opposite of this is how motors will produce electricity. All right, now we're going to move into the practice problems. I believe I have 2 of them ready to go over with you. The first one states, what is the force of a proton moving 3,450 meters per second at an angle of 35 degrees into a screen that has 1.75 Tesla magnetic field that points to the left? All right, so what we're first going to solve is the force, which is the equation that we talked about on the slide right here. So we're going to plug in what we know. Remember, Q is that constant that we talked about in that first lesson. If you haven't watched the first lesson, make sure you go back and write down this on your formula sheet. V is the velocity, which is given to us in the problem. And then now we have the sine angle. Again, it's given to us in the problem. If it's not given, please assume that it's perpendicular. So we plug that into our calculator and we should get 5.55 times 10 to the negative 16 newtons for the force. Remember that fingers point to the left, the direction of the field. The thumb points into the screen, the direction of the velocity. So your palm points upward in the direction of F. So remember that you have to have a direction because it is a vector quantity. So we have a force and then the direction will be upwards because of the right-hand rule. What is the magnitude of a charge if a force of 2.15 newtons is applied upward when traveling 31.4 meters per second at 68.2 degrees to the left of a 0.0421 Tesla field pointed into the screen? So first we're going to find the charge here. So we're going to rewrite the equation. 2.15, which is given to us in the problem, of the force divided by the product of 31.4 times 0.0421 sine 68.2. Again, given to us in the problem, we should get 1.75 coulombs as the charge. So again, if you're using your right-hand rule, the fingers are going to point into the screen. Your palm is going to point upward, and then your thumb is going to point left. So the velocity is given as bright, so the charge must be a positive 1.75 charge. Now, if it was pointing to the left, the answer would be negative. And again, remember that the positive and negative would give you direction, so this would be the correct answer. That is it for this lesson. Please let me know if you have any questions after watching this. Thanks.